chapter 2. So chapter 2 is where you actually get into like calculus stuff that was covered in pre-calculus a little bit, but it's also like the first step in calculus. It's limits, area under the curve, and a little bit of finding slopes. So it starts off with area under the curve, which I don't really like, but I'm gonna, I guess, continue to do that because that's how we learned it. Area under the curve, there are different methods of doing it. Left endpoint is when, let's say we have the interval from here to here. Left endpoint is you use the left part of the rectangle to as the same as the point on the curve. So this is the left endpoint of the rectangle, and it's on the curve. The right endpoint isn't though, because it's a rectangle and it's both points can't be on the curve unless it's a special case. But then the second rectangle has its left endpoint on the curve. Third has its left endpoint on the curve. And they should all be equal widths. It's just a bit hard to draw on the computer screen. Fourth also has a left endpoint. Fifth also does. Sixth also does. And how many other rectangles you want? The left endpoint will always be on the curve. On the other hand, right endpoint is when the right endpoint, as you might imagine, is on the curve. So this is a right endpoint rectangle. This is also one. It's approximately on the curve. It should be fully on the curve, but again, it's hard to draw. So that's also a right endpoint, and so on. So in this case, I'm just using 6 rectangles for both of them. Now, as you might see, this is a key point later on. When you're using left endpoints, you get an underestimate because there are these parts of the area that you haven't gotten to. And when you're doing an overestimate, when you do right endpoints, you get an overestimate. This isn't always the case though. When you're having an increasing curve, left endpoints give you an underestimate. But if you're doing a decreasing curve like this, left endpoints give you an overestimate, as you can see here. So that's an important distinction to make. I won't go in detail into the formulas, but they're very similar formulas. It's just I is equal to 0 to n minus 1, where n is the number of rectangles for left endpoint, and it's from 1 to n if it's right end. What's inside the summation notation doesn't really change. We have the width, which is delta x, times each of the heights. So it's f of, because the height is on the curve, f of delta x, the width, times I, or k if you want, plus your original starting point, a. So that is basically the formula. And for notice, delta x is equal to b minus a over n, the number of rectangles. So where b is the upper bound, a is the lower bound, n is the number of rectangles. And that's the formula for left endpoint. Again, for right endpoint, it's I equals 1 to n, but the inner part stays the same. I'm going to go over the other methods really quickly. There's the midpoint, and there is a way to do this with keeping the inner the same, and it's from 0.5 to n minus 0.5. And that's, strictly speaking, not how you're supposed to use summation notation, because it's supposed to be in whole numbers, but it works on a calculator. You probably shouldn't do it on the AP test though. Instead, what you would do is you would do summation from I equals 0 to n minus 1 of, again, delta x times f of delta x times I plus 0.5. So it's the same thing as we did when we changed the summation, the index values from 0.5 to n minus 0.5. But in this case, we're doing I plus 0.5 instead of just I. So now when I is 0, it's actually 0.5. When it's n minus 1, it's actually n minus 0.5. So it's the same thing, but it's neater notation and more mathematically correct, if you will. And then again, you add a, and again, delta x is equal to b minus a over n. Finally, we have trapezoids. Trapezoids basically look like this. And of course, they look a bit more accurate than rectangles. I forgot to show you an example of midpoint. Midpoint rectangles have the midpoint on the curve. So it doesn't look like a great estimate, but actually most of the time, whatever is above the curve is also below the curve. Above the curve, again, this isn't accurate, but it kind of matches up, and it's very similar to trapezoid in accuracy. Depending on the type of curve, you would want to use one over the other, but trapezoids and midpoint rectangles are much better estimates than left endpoint and right endpoint rectangles. Trapezoids, you can use the trapezoid rule, which basically states that the area is the width over 2 times the first value plus 2 times the second value. So a plus delta x, because delta x is the width of each rectangle. And then 2 times every value in between, plus 2 times the last by 1 value, plus the last value, just 1 times the last value. And that's the trapezoidal rule. Again, important in calculus, probably didn't learn it in pre-calculus though. So this might be new. But you can also use summation notation for trapezoids. I wouldn't, because it just looks very long and very difficult to do. But you can, I won't show it here, but you can use summation notation for trapezoids.
I had a question about like trapezoids, LRAM and RRAM, and midpoint actually. So like, when are all of them like overestimates and when are all of them like underestimates? And like, which one's like the biggest, like right or like trapezoid or like left?
So to answer Arif's question about the different methods and when they should be used, let's talk about LRAM and RRAM first. So LRAM is left endpoint and RRAM is right endpoint. When you have an increasing curve, so when it's increasing and when it's decreasing, that's when there's a difference between LRAM and RRAM. When it's increasing, so something like this, that means that LRAM is going to be an underestimate. And RRAM is going to be an overestimate. So RRAM is going to be greater than LRAM, no matter what, if it's increasing. Now, what happens if it's decreasing? If it's decreasing. LRAM this time is going to look something like this, because the left endpoint is still on the curve. This means it's an overestimate. And RRAM is an underestimate because the right endpoint needs to be on the curve, which means the left endpoint has to be lower than the curve. So now LRAM is going to be greater than RRAM no matter what, and it's always going to be an overestimate. Now, what about trapezoid, which I like to call TAM, trapezoid area method, and MRAM, or midpoint area method? This time, it doesn't matter whether it's increasing or decreasing. Instead, it matters if it's concave up or concave down. Now, we didn't really talk about concavity, but concavity, basically think of it like a parabola is concave up because it's facing upwards. The negative x squared, the downwards parabola, is concave down because it's facing downwards. That's not really a good description, but it's kind of like if you're driving in a car around a curve, which way are you leaning? So if the curve is like this, you're leaning to one side, and if the curve's like this, you're leaning to another side. So that's basically another definition of concavity, like that, I guess, is easier to understand. But this makes either trapezoid or midpoint an overestimate or underestimate. Let's talk about concave up. If it's concave up, trapezoids are going to look something like this. This is an exaggeration. Obviously, trapezoids shouldn't be this big when you're doing calculations, but it goes to show that trapezoids are going to be an overestimate when it's concave up. On the other hand, midpoint rectangles, and this is very hard to show because there is no like one place where it's off here and here. They usually make up for each other, but it's an underestimate in concave up situations. It's hard to show, but if trapezoid is an overestimate, midpoint must be an underestimate. Let's look at a concave down situation. We have trapezoids here and a trapezoid here. Now trapezoid is an underestimate in a concave down situation. And in a concave down situation, midpoint is going to be an overestimate. Again, hard to show, but it's going to be the opposite of whatever a trapezoid is. So these two are going to be closer, though, to what the actual value is. So depending on the curve, if it's concave up and increasing, for example, this is concave up and increasing. You can also have concave down and increasing. So this is like a square root curve. you're concave down, but the x values are still getting, sorry, the y values are still getting larger. Based on that, you can decide whether LREM, RM are overestimates, underestimates, and whether trapezoid, MREM are overestimates, underestimates. And one last thing I forgot to mention about trapezoid, it's going to be the average of the LREM and the RM. So if these are the LREM and RM, the average of those is going to give you the trapezoid. Just putting it out there. So there's no set order for which one is the least and which one's the greatest. It matters on the situation. And you can't really even compare them because LRM and RM depend on increasing and decreasing, while trapezoid and midpoint depend on concave up and concave down. So you can't really compare these two with these two. Okay. The next part of chapter 2 goes on to limits. Limits was introduced in pre-calculus, but I'll briefly go over it as well. Limit is basically as x approaches something, what does y approach? Limit as x approaches 2 of x squared is a pretty straightforward limit. You can just plug it in. 2 squared is 4, and you'll get an answer. There are other limits that you can't do this with, and that's what we'll be getting into next. But before that, let's look at limits on a graph. Limit as x approaches 2 of whatever this graph is going to be this point that it is on the graph. But it's not always the case. And we'll get into discontinuities later once we talk about continuity. But before that, we have to talk about indeterminate forms of limits. The most common one is 0 over 0. And there are a few techniques on how to solve it. So let's say we have another limit as x approaches 2. But this is of x minus 2 over x squared minus 4. Let's try plugging it in like last time. As we put 2 in the numerator, we get 0. Okay, fine, maybe the answer is 0. But we put 2 in the denominator. We get 4 minus 4 is 0. We have an indeterminate form. Now, we can't just write is equal to 0 over 0 because that's undefined and nothing can equal 0 over 0. So we have to simplify a bit. There are two main techniques and some other side techniques as well. The first one's factoring, where you want to factor either the numerator and slash or the denominator to cancel some terms out and be able to substitute. The second one is conjugates, and we'll get to that later. But let's try factoring. X minus 2 over, we can factor the denominator. It's difference of squares, so it's x minus 2 times x plus 2. And now we see an x minus 2 that we can cancel out, and we're left with limit as x approaches 2 of 1 over x plus 2. You can't ignore the limit symbol here. You can't just say, oh, this is equal to 1 over x plus 2. You have to put the limit before the 1 over x plus 2, because you can only simplify this when there's a limit. Otherwise, you're going to also have to state x cannot be equal to 2. And it's like that thing I told you about rational functions, where you can cancel stuff out to get a whole, but you also have to specify x is not equal to this value. Plugging in 2 now, you actually get a value. You get 1 over 4 as your answer. Conjugates is where it's similar to factoring, and you can actually use factoring in a conjugate situation. But conjugate is basically where you multiply it. So if you have x minus 2 over x squared, x minus 4. This is an example as limit as x approaches 4, for example. This is where you can use conjugates, where you multiply top and bottom by root x plus 2 over root x plus 2, cancel some stuff out. But you can also use factoring. You can use difference of squares. Even though x really isn't a square, you can say it's square root of x squared, and use square root of x minus 2 times square root of x plus 2, because that's difference of squares, and then cancel that. So you can use factoring in conjugate cases. So if you just want to memorize one technique, factoring is the way to go. Another indeterminate form is infinity over infinity. And this is where dominant terms come in. I mentioned it earlier when we were talking about horizontal asymptotes and end behavior asymptotes, but limit as x approaches infinity or negative infinity of a function will make you look for dominant terms. If it's just polynomial over polynomial, we just use the end behavior asymptote rules we learned. But if there's something else, such as 2 to the power of x, that's when we use dominant terms. the order goes from logarithmic to power or polynomial to exponential. Exponential is the greatest. For now, we'll learn about things later in calculus and beyond about faster growing functions, but for now, exponential is the greatest, logarithmic's the least. So whenever you have something like this, exponential is going to be the dominant term if it's there. Next is power, and within power we have like x squared and x cubed. X cubed is the more dominant term, and then after that we have logarithm. Pretty simple, but there's one little caveat. When we're going to negative infinity, exponential is not dominant anymore, because as we go to negative infinity, 2 to the power of x approaches 0, because it's something like this, not like this. So as this goes to infinity, the other side goes to 0, and therefore it's not a dominant term anymore. We're looking for what goes to infinity or negative infinity when the limit goes to infinity or negative infinity. This goes to 0 and therefore is invalid, cannot be used as a dominant term. So be careful when it goes to negative infinity. And yes.
Oh yeah. So like the graph would basically go to, like, for the last problem, it says
Yeah.
x squared divided to x to the power of x, right? So if it goes to negative infinity, if this go to infinity, right?
Right, because this goes to 0, so you can discount that. This goes to x squared, so since it's squared,
Yeah.
negative infinity squared is positive infinity. So yes, it does go to positive.
Okay. Yeah, it does not exist, but y goes to infinity. That's how you write it, right?
Right, exactly. You would have to write it as dne, but y approaches infinity. And technically you can write equals infinity, but in some cases you cannot write that. Like if your teacher doesn't want you to, like Mr. Ogle doesn't want you to write it as equals infinity, you have to write it like this.
Yeah. All right, thank you.
And then we have to talk about continuity. So continuity is, we talked about earlier, continuity is basically, it has to like be such that you can draw without lifting your pencil. But a more formal definition of continuity uses 3 steps. The first step is that the limit exists. And I'll talk a bit more about how you identify if it exists or not later. Second one is that the function at that point exists. And the third one is that whatever you got in 1, the limit, must be equal to the f of the function at that point. Now, obviously, this is not how you write it, but I'm generalizing for all points. So I guess I could have written a in here for all points, but these are the basic criteria. Now, how do you find out if the limit exists or not without looking at a graph? Well, the limit exists if it's one-sided limits exist. So as x approaches 2, for example, minus must be equal to the limit as x approaches 2 plus. The minus represents from the left side, plus represents from the positive side or from the right side. And if they converge at the same point, then the limit exists. And notice I left a big space here. You can just put whatever function you want in there. So a few examples of discontinuities. We have some important ones. So this, when you have this, is called a jump discontinuity. This fails criteria 1 because it the limits are not equal to each other. The one-sided limits are not equal to each other. Therefore, the limit doesn't exist and it fails criteria 1. This, when there's a hole in it, is called a removable discontinuity. This time the limit exists, but the function doesn't exist at that point. So this is 2. It doesn't work for 2. You can also have a hole like this and this, and that's also technically a removable discontinuity. And this fails criterion 3 because the function does exist at that point up here, but it is not equal to the limit. It's off the normal function, so it's not equal to the limit and therefore fails criterion 3. Finally, there's an infinite discontinuity, or basically an asymptote, a vertical asymptote. This also fails criterion 1 because the limit doesn't exist at that point and therefore fails criterion 1. Any questions so far?
No.
Okay. One final thing I wanted to talk about, the intermediate value theorem before the final thing is basically stating that when you have a continuous function, this is important, when you have a continuous function and it goes from some value f of a at point A to some value f of b, point B, and it's continuous, remember that, the function must go through all the points, all the y values between these 2 points at least once. It can go more than once, something like this, but it has to go at least once. Even if it's just a straight line, it has to go through all of them at least once. This is good for finding roots of functions. If you know two close by x values are on opposite signs, it must go through the x-axis at some point, which means there must be a root at some point between those two x values. Now, what if it's not continuous? You can have something that looks like this, and it's a non-continuous function, and it doesn't go through all the points. So that's why it says it has to be a continuous function. I saw someone raise their hand.
Yeah, so like, is the question supposed to tell us the function is continuous? Like, if it doesn't say that, do we just say not enough information?
Yes, exactly. You might think it's not that big of a deal, but if the question doesn't say it's continuous, you say not enough information, it doesn't have to follow the intermediate value here.
Okay.
That's a big thing.
And if I have to like write an explanation, do I have to say like, since the function f of x is continuous on the intervals bracket begin a comma b, and that the point, like whatever the thing is, or like the root lies between a and b, it must cross through the x-axis, and there must be one root. Like, do I have to say
Yeah,
it like that?
and it doesn't always have to be a root. You can just say this function is a continuous function and therefore follows the intermediate value theorem, which states that between any 2 points a, b, such that the function is continuous on the interval a, b, square brackets, all the points between f of a and f of b must be visited at least once. That's basically your explanation.
Okay, thank you.
And that's basically all of chapter 2. There are some other topics such as trig limits, but that was also in pre-calculus. So I'm not going to go through them that much.